Let's now look at modularized ASR systems, and these systems are also called hybrid ASR systems. The first component of modularized ASR system is acoustic model. The job of acoustic model is to generate probability distribution over sound units in the language. So for example, for English, the sound units could be a, ma, ka, ta, pa, ba, etc. So at every audio frame, acoustic model would consume the audio features corresponding to that frame and generate the probability distribution over sound units. So before we get into more details of acoustic model and its training, let's look at how the training data of ASR would look like. So you would have n number of audio examples, which could be like 1 million audio examples or like 10 million audio examples. And for each audio example, you would have the corresponding transcript. So before we kind of start training the acoustic model, we would convert the true transcript corresponding to audio into the sound units of that language. So for example, the transcript and could be converted into sound unit a, na, and da. Now let's look at an example to see how we train acoustic model. So say we have an audio which is divided into 7 audio frames. So we have frames x1 to x7 corresponding to this audio. And say we have another model called alignment model, which will take the input as sequence of audio units in the transcript and tell us from what frame which audio unit was spoken, right? Because in the training, what we have is the audio and the corresponding transcript. The training data does not contain information like from frame 1 to frame 3, I spoke sound unit 1. From frame 4 to frame 5, I spoke sound unit 2, and so on, right? So we use this alignment model to kind of get at each frame what was the sound unit spoken given the transcript of the audio, right? Now, what we do is at every frame, we have the audio feature computed. So we pass the audio feature through an acoustic model. It is also sometimes called audio encoder. And we would get an audio embedding at every frame, right? And this acoustic model could be an LSTM or could be a BLSTM or it could be a transformer. Now at every audio frame, I have the acoustic embedding. So I can pass the acoustic embedding to a softmax, and the size of this softmax is going to be same as the number of different sound units that I want to represent in my language, right? So let's say for our example, we have 3 different sound units in the language. This is just an example. You are going to have way more than 3 different sound units, but let's assume that you have just 3 different sound units. Then the softmax would give the probability distribution over these 3 different sound units at each of my frame given the current set of the parameters of acoustic model. And I can do it for each of my frame, and then I can compute a cross entropy loss because I know from the alignment model that what should be the sound unit here in a given frame and what is the probability distribution being generated at that frame given the current set of parameters. And then I can use the cross entropy loss to maximize the probability corresponding to my true sound unit at that particular frame, right? And you compute the cross entropy loss for frame 1, you do it for frame 2, you do it for frame 3, up to all of your frame, which are like 7 frames here. And this would be the total cross entropy loss across these 7 frames would be the cross entropy loss for this particular audio instance. But in training, you would be creating batches of many audio examples or audio instances. So you would compute cross entropy loss corresponding to each of your audio example and try to minimize the loss, so that in future iterations of training, you are giving more probability to the correct sound unit at a given frame, right? So once we have finished this training, we would have a model which could take in the audio features corresponding to a frame and generate the probability distribution over the audio or the sound units in the language. Let's look at other components of modularized ASR system. Acoustic model, as we looked in previous slide, would give us probability distribution over different sound units at each of our audio frame. Then we have pronunciation model. Job of pronunciation model is to tell us what are valid sequences of sound units that would constitute valid words in the language. For example, a sequence of sound units va, a, ta would constitute a valid word what in English, whereas a sequence of sound units ja, za, ma, za, ka, ta, pa would not constitute a valid word. The pronunciation model assigns a score to sequence of sound units based on how likely that particular sequence of sound units is going to form a valid word in the language. The next component is language model. Job of language model is to assign a probability score to a sequence of words based on how likely that sequence of word is going to appear in the language. For example, how are you is a more likely sequence of words than how is you. Language model can also be thought of as predicting probability of next word given a sequence of words as history. For example, given the history of what is the weather, next likely word is going to be today, tomorrow, or in rather than hello. Let's now briefly discuss how these components are grouped together. This in itself can be a lecture, and since focus of this lecture is RNNT based ASR system, which is non-modularized ASR approach, so we are not going to get into details of modularized ASR decoding in the current lecture, but here is a summary of how it works. We use decoder, a graph-based component, to do composition of acoustic models output, pronunciation model, and language model. We do beam search to pick most likely transcript candidates at each audio frame. In the end, from the last audio frame, we pick the transcript candidate which has highest score in the beam search and call it our final transcript. For example, the final transcript for a given audio could be the cat set. That was the modularized ASR system where we have different components which are built separately and then are put together using the decoder to get us the transcript with the highest probability as the spoken transcript from the audio. Then we have non-modularized ASR training where we would have just a single neural network which would be able to convert the audio features into a final spoken transcript. So in order to train the non-modularized ASR system, we would replace sound units such as phonemes by letters and formulate ASR as a sequence-to-sequence problem.